Join us today as we delve deep into the secrets of the nature of the universe, exploring relationships between what we see and what we feel around us. Welcome to Unit 21 of Astronomy, the dual nature of light and matter. You may have often wondered how scientists are able to study solar systems and suns halfway across the universe. Even though they are separated from these bodies by hundreds of millions of miles, scientists can still know how hot a star is, what elements it is made up of, and a myriad of other characteristics. The answer to this question is light. Light is a unique phenomenon in the universe which provides the key to unlocking and understanding vast amounts of knowledge locked deep within space. Light is a form of radiant energy which can travel without a physical connection. Something like sound, for instance, can only travel with a physical connection, such as air, through which the energy can be transferred. Thus, astronauts in space can see light but cannot hear sounds. Light travels at approximately 300 million meters per second in a vacuum. That's 186,000 miles per second. It is a strange substance which behaves differently at a quantum level. Light is an example of a substance which exhibits wave-particle duality, which means that it is best modeled as both a particle and a wave. As a wave, light is a mix of electrical and magnetic forces which creates a cascade of disturbances through space. Electric fields create magnetic disturbances which create electric fields and so forth, giving light the name electromagnetic wave. As such, light can interfere with itself like other waves. For example, ripples in a pond. If a ripple is made without other waves, it proceeds outward from the source. However, if there is another wave present, the waves will cancel each other out at certain points, called bands of interference. On the other hand, light cannot have fractional proportions of energy, something a water wave can have. Light only increases its energy in fixed intervals, which are called photons. Photons are the quantized particles of light which represent the most basic piece of light energy. This explains the nature of fractional components, as one cannot have a piece of a particle. The following is an example of how this wave-particle duality works. As we can see here, if particles are shot from a source toward a wall with two slits in it, we would expect the distribution of particles on the other side to be random. Now, if we were to shoot a wave toward the two slits, we would expect to see interference among the two waves which would result from the slits, much like with the ripples in the pond, creating vertical bands of detection with the spaces in between the result of cancelled waves. An object with wave-particle duality shot through the same two-slit experiment behaves like both of these objects. The object moves forward like a wave, creating zones of interference after the slits where it cannot be. However, when it hits the detector, it becomes a single particle, creating one measurement point where the wave is strongest. If this is done repeatedly, the particles are randomized, but only in vertical bands, and not in the region where interference canceled the waves. Light is also affected by distance. After light is emitted from a source, the photons maintain their speed and energy, consistent with Newton's first law. However, as they cover more distance, they spread out, with the photons per surface area decreasing with the distance squared. For example, imagine 4 photons were emitted from this light. At 1 meter away, they would have spread out to be near the corners of the meter-wide detector, and we would have 4 photons per square meter. However, if the distance were double to 2 meters, there would need to be an area 4 times as large to catch all the photons, resulting in only 1 photon per square meter. This holds consistent with the inverse square law, which predicts that the brightness equals the total output, in this case 4 photons, divided by the distance squared. Moving on, we now examine how light and atoms interact. Atoms, which are the smallest pieces of elements, are made up of a nucleus and electrons, with the electrons orbiting the nucleus. Elements are made up of one type of atom and are determined by the number of protons, while chemical properties are determined by the electrons in orbit. Electrons, like light, have wave-particle duality. All matter, in fact, behaves like waves in some ways, but only at the smallest levels. As electrons are both waves and matter, they can only orbit in quantized orbits called energy levels. An atom's ground state is when all of the electrons are in their lowest possible energy level. The smallest energy level is only 1 electron wavelength long, which prevents the electron from approaching the atom any further. In terms of light's interaction with atoms, the actual interaction depends on the type of atom. Electrons in an atom can jump up and down through energy levels, but need energy to jump up while releasing energy in the form of light as they jump down. In order to make an electron jump up, it requires a very specific amount of energy. As this diagram illustrates, in a hydrogen atom, with a single proton in the nucleus orbited by a single electron, it takes approximately 10.2 electron volts for the electron to jump up to the next highest energy level. This is called absorption and puts the atom into an excited state. The atom now has more energy and tries to lose it by having the electron jump back down into its lower energy orbit. This excess energy in turn is emitted as light, with the color depending on how much energy is released. Depending on the amount of energy inputted into the atom, the electron can jump 2 or even 3 levels, which in turn causes it to release different colors of light upon jumping down. Here is an example of a full spectrum of colors from light ran through a prism. However, when light from excited hydrogen is sent through the prism, it only produces 3 colors of light, called line spectra, which correspond to the 3 possible energy jumps. The other light which originally passed through the atom was the wrong energy and could not be absorbed, and so was not re-emitted. Other examples of emission include the aurora in the atmosphere, as well as the flame from a burning candle. This concludes the information from astronomy, Unit 21, the dual nature of light and matter. I hope you enjoyed the presentation. Thank you for watching.